Hello, this is Zhice Yang from ShanghaiTech University. In this talk, I will report a new type of covert and set channel. This channel makes use of the processor idle power management mechanism. It is not based on cache or memory. It works across cores and processors of the same physical machine. At the same time, it can bypass VM isolation. We verified this channel with in-house testbed and dedicated host in the public cloud. Power efficiency is very important for modern processors. They use sophisticated mechanisms to conserve power. When executing instructions, processors are in the active state. There are mechanisms managing the power of the active state, such as DVFS. Related security implications have been explored by the literature. In this talk, we will focus on the idle state, where the processor has nothing to execute, but its hardware still consumes power. Idle power management is designed to turn off the hardware component of the idle processor to reduce its power. A multi-core processor consists of the cores and the Uncore. The Uncore represents the hardware component shared by the cores, such as the memory controller, the last level cache. When considering turning off the hardware component of the processor, it is necessary to consider the dependency between the core and the Uncore. First, the Uncore must be active when any of the cores are still active. This is straightforward, since it causes functional problems if we turn off the Uncore component when a core is still active. On the other hand, to reduce the power consumption, it is necessary to turn off the Uncore if all the cores are idle. Therefore, the Uncore's idle power status is somewhat slaved or determined by the idle power status of the cores. This is the idle power dependency between the core and Uncore. Such a dependency leads to a new type of covert and set channel. The idea is to use the Uncore to spy the activity of the core. Let's consider the processor with 4 cores. By default, all the cores are idle. The whole processor is turned off since there is no load. Then we apply the workload to core 0. Core 0 and the Uncore become active. The remaining 3 cores are still idle since the workload is not executed by them. In this case, we note that the process on the 3 idle cores are able to infer the activity of core 0 through spying on the power status of the Uncore, since the Uncore activity just mirrors the activity of core 0. Next, we talk about how to extend the above idea to launch practical attack on virtual machines in multi-tenant cloud. First, we consider the covert channel between 2 co-located VM guests. The source process in guest A wants to send a message to the source to the sync process in guest B. Even though they cannot talk to each other directly and may be assigned to different physical cores, the source can encode information into its workload pattern, which will stimulate the Uncore shared with the sync process. If the sync process is able to probe the activity of the Uncore, then it can receive the encoded information. However, the problem is how to probe the status of the Uncore in a fully virtualized environment. The VM hypervisor only exposes very limited information about the physical processor, which is the main obstacle. Our idea is to use some VM perceivable metrics. To explain that, we need more knowledge. First, we take a look at the idle power management of individual core. Core low power idle state, or core C state, define the levels of turning off of the core. Larger value of the C state indicate more components of the core are turned off, and hence more power saving. The negative impact of deeper turning off is that the core takes more time to fully restore to the active state. So to balance the power efficiency and the system performance, when the load is light, the cores tend to stay in deep C state. When the load is intense, the cores tend to stay in light C state. The idle power management of Uncore is less transparent as it is mainly controlled by the processor firmware. According to our investigation, there are several mechanisms affect the Uncore idle power. They at least include the package C state and the Uncore frequency scaling. Even though the mechanisms are not fully transparent, the primary rule is similar to the cause. The deeper the Uncore sleep, the more time it takes to restore to the active state. So our approach is to measure the latency of the Uncore to guess its power status. In order to do that, we take advantage of the timer. Timer interrupt is generated by the timer hardware of the physical machine. When the timer fires, its interrupt is subject to different levels of delay. Such delays are contributed by both the core and Uncore. We measure the decoupled latency with respect to different idle power status of the processor. The deeper the sleep, the larger the latency, as expected. Here comes an example of the Covert channel. First, we use the loaded execution of the source process to represent bit 1. At the same time, the sync process measures the timer latency. We note that since the measurement does not introduce too much overhead, core 3, which is responsible for the sync process, is almost idle. So in this case, the timer interrupt scheduled by the sync process are directed to core 3, and thus the latency is introduced by the active Uncore and the idle core 3. We use the sleep of the source process to represent bit 0. Since the Uncore is no longer stimulated by the source process in this case, the timer interrupt of the sync process are delayed by the idle Uncore and the idle core 3. Compared with the previous case, the timer latency is larger. This is because the idle Uncore contribute more latency. And so on. The source process can encode the workload to stimulate the Uncore so that to convey information to the sync process. We verified the above covered channel with different platforms. It can achieve a theoretical throughput of more than 2 kbps on desktop platforms. Its performance is affected by several factors, such as the processor architecture and the operating system. The performance is worse on server platforms. This is because the server CPUs are more performance-oriented and do not tend to sleep in deep idle state like desktop CPUs. The Covert channel also can be observed across socket, as shown in the right figure. This is because even all the cores of the processor 0 are idle. Its Uncore must stay active to support remote memory access from processor 1. We note that this behavior lasts even when we adopt NUMA strict policy to restrict the remote memory access. We verified the Covert channel with dedicated host in public cloud. The raw timer latency trace of EC2 is shown here. Since the cloud servers adopt performance-oriented power policies, the channel has a limited capacity of several BPS. The channel can be used to spy on the activity of the co-located VM guest. The attacker achieves this through probing the activity of the Uncore, which reflects the activity of the victim. As a preliminary example of the SAT channel, the attacker tries to extract the timing of SSH keystrokes of the co-located VM guest. We observe that the processing of SSH keystrokes expose a unique time latency footprint. We use it as the template to differentiate the keystroke event from the background noise. It is possible to further extend this attack to launch keystroke timing attack. To eliminate the aforementioned covert and set channels, the VM administrator could limit the time resolution of the guest or adopt performance-oriented power plans. The attacker can also be detected through the abnormal interrupt rate. In this talk, we report a new type of covert and set channel that based on the idle power management dependency. The course activity is reflected in the idle power status of the shared hardware, such as the Uncore. Further, in a virtualized environment, the idle power status can be probed through the time latency. So thank you, and I'm happy to take questions.